Yes, welcome back to TRB Polytechnic EEE Solutions. So let us get into the next problem. Yes. So it's a lag lead network. Okay, the phase lag lead network shifts the phase of a control signal in order that shift the phase of the control signal in order that the output phase becomes what? It's a lag lead network. Okay. All frequencies becomes independent of frequencies, leads at low frequencies and lags at high frequencies. Yes, we should know. Okay, so without knowing a lag lead network, we can't conclude the problem. Okay. But one thing is for sure. Okay, so at center frequency, it is going to neither lead or nor lag. Okay, it is going to offer a zero phase shift. If you remember the circuit, you can play with that. The circuit is very simple and probably you used it in Wien bridge oscillators, the same circuit. So you have R and C parallel, R and C in series. That's a circuit. So what we have is, so this is the supply voltage V in of S. So R and C in series. Let this impedance is 1 by SC, then R and C in parallel. Okay, so then I have R and C. That's a network we usually use in Wien bridge oscillators, especially to offer the feedback. Same circuit you can use. That's exactly lead lag network. Okay, or lag lead lag. Anyway, you can pronounce this, no problem. Okay, S into C. That's your output V naught of S. You can go for the transfer function. With that, you can conclude things. Okay, what happens during low frequency? What happens during high frequency? Something new means you should be capable of beginning from the scratch. Okay, so take Z1 of S as R plus 1 by SC. So that means this is your Z1, let me say. So let this is Z1. Let this is Z2. Okay. That gives a circuit like Z1, Z2 excited by Vn. So this is Z1 of S. Let me conclude that's going to be SRC plus 1 by S into C. And Z2 of S is going to be R parallel 1 by SC. As a result, you will end up with R by, okay, multiply, you will end up with, so R into 1 by SC by R plus 1 by S into C. As a result, you will end up with R by SRC plus 1, then play for Z1 plus Z2 of S, nothing but SRC plus 1 by SC plus, okay, let me take here R by SRC plus 1. Okay, that's your Z1 plus Z2. I need this. That's why I'm going for that. So then what is that? Z1 plus Z2 will be equal to, taking LCM, it's SC into SRC plus 1. As a result, SRC plus 1 the whole square plus SRC will get. Why you need this? Because V naught of S by potential division is V in of S into Z2 divided by Z1 plus Z2. Yes, you need Z1 plus Z2. Z2 is already available. We'll go for the transfer function V naught by V in. So V naught by V in. Let me check. Yes, I'll go for a space. So what is the transfer function? V naught of S by V in of S will be Z2 of S by Z1 of S plus Z2 of S formally. So what's Z2? Z1 plus Z2 already we know. What is Z2? That is R by SRC plus 1. So numerator will be R by SRC plus 1. That's a numerator. Denominator will be Z1 plus Z2 already we know. Expand it. So okay, let me write it here. SRC plus 1 the whole square plus SRC divided by SC into SRC plus 1. This and this will get cancelled and SC will move to the numerator. Therefore, the transfer function V naught by V in of S will become, it's SRC the whole divided by, expand this remaining, so you'll end up with SRC the whole square plus 2 SRC plus 1 more SRC, 3 SRC plus 1 you will get. That's how we get. Okay, so B blind set S equal to j omega. So V naught by V in of j omega, that's your transfer function. Numerator will be j omega RC divided by 1 minus omega RC the 1 minus omega RC the whole square. Okay, that's a real part. Okay, and plus j3 omega RC. Now what we talk about is let omega RC is equal to 1. Okay, that means omega equal to 1 by RC. Then tell me what is your V naught by Vn. Okay, V naught by Vn is equal to, yes, real part is vanished means you will get 1 minus omega RC the whole square is 0. Then j omega RC by j3 omega RC will give 1 by 3. Then put it in polar, it's 1 by 3 angle 0. That's what I said. So at this particular frequency, it is offering neither lagging angle nor leading angle. So it's all about omega less than this. So play for omega less than this, omega less than this center frequency. Let me take it as a center frequency, omega C. So omega C is 1 by RC. So less than this, omega less than the center frequency, what will happen? So omega less than this means omega less than omega C means omega is less than. So here omega RC is equal to 1 means omega is equal to 1 by RC. If I choose omega less than this means omega RC will become less than 1. Okay, the point is this. Okay, so omega is going to be less than omega C means who is omega C? Omega C is 1 by RC. Then what is omega? Therefore, what it mean? Omega is less than 1 by RC. That's what it means. If omega is less than 1 by RC, what is that? 0.1 by RC, 0.2 by RC, like that. So that is going to be omega RC will be less than that. Omega RC less than 1 means it is going to be real. Okay, it is going to be positive real. So it is a positive real means, so resembling the situation, for example. So 1 minus omega RC the whole square means assuming it is almost omega RC 0 also belong to that only. So let omega RC equal to 0, then it is going to be omega RC 0 means this is also going to be 0. Some omega RC number you can assume. Say for example, omega RC is equal to, instead of 1, let me take, okay, omega RC is less than 1. Let me take, okay, omega RC less than 1 and omega RC more than 1. That's a question. Okay, so automatically omega less than 1 by RC, omega greater than 1 by RC you will get. Okay, yes, we'll go with that. Omega RC less than 1 means, let me take for example any number which will give a round number. Okay, 0.6 let me take. Okay, 0.6 means then what's my transfer function? V naught by, only for the conclusion sake, V naught by V in of j omega will be equal to, what is the numerator? J 0.6. Denominator will be 1 minus 0.6 square is going to be 1 minus 0.36. So it's going to be 0.64 plus j what? 3 times omega RC. So 3 times 0.6, 1.8, like that you will get. What is the numerator angle? 90 degree. Okay, because it is j. Denominator angle, this will be anyway less than 90 degree. This will be anyway less than 90 degree for sure, because its angle is real plus imaginary. That is going to fall in which quadrant? Real, positive real, positive imaginary means it is going to fall here. This quadrant is going to have angle only between 0 to 90. Therefore, definitely it is less than 90. Therefore, if you bring that angle to the numerator, it will be minus of that. So assuming it is, for example, 30 degree or 40 degree, then 90 minus 30 or 40 will be a positive angle. So that means conclusion is this. So omega less than 1 by RC, low frequency, it is going to act as the lead compensator. Low frequency, so this is your region. Okay, so this is your omega 1 by, that's your omega 1 by RC. That's no phase shift. So here it is going to be lead and here it is going to be lag. You can confirm. Okay, you can check it. So as of now, I'm concluding low frequency it is going to act as a lead compensator. High frequency it is going to act as a lag compensator. It's confirmed by placing certain value for omega RC. Okay, right? So strongly I'll go with the option. You can choose. I have given whatever the proof needed. You can choose the answer simply. Yes, it leads at low frequencies and lags at high frequencies is the right answer for this. Without this, you can't. Okay, right? Yes, that's an interesting problem on lag lead network. For that, you should know the lag lead network. Yes, try to Google what is your lead network, what is your lag network. Know them. So with that, you can answer any other problem which happens in future. Okay. Yes, next problem. Yes, the overall transfer function of a control system is given below. Then the resonance peak. Okay, so again, he's playing in the frequency domain. So it's for a second order system. So he's talking about resonance peak. So resonance peak is valid. That is going to have a number that is going to be k by 2 zeta into root of 1 minus zeta square. People usually won't go with the k. So for that, the k is the static sensitivity. Okay, so k into omega n square divided by, in this case, that k is equal to 1. So since k is equal to 1, MR can be simplified. But don't remember, MR with always numerator 1, this is the best expression for the MR resonance peak. Okay, so that means what we have is we have omega, and this is your M of a MdB of M of a second order system. So then it may have a maximally flat response, butterworth response, or it may have a Chebyshev response with resonance like this. So this is what exactly the frequency known as omega or resonance frequency, and this is what we call as resonance peak. That resonance peak only I'm talking. If DC gain is k, it is going with this expression. If in this case DC gain is 1, therefore the expression for MR is 1 by 2 zeta into root of 1 minus zeta square. Zeta is a damping. So compare the given transfer function, the transfer function T of S with what? 25 by a square plus 5 into root 2 times s plus 25 with k into omega n square by a square plus 2 zeta omega ns plus omega n square. Okay, so now you know your omega n. Problem is, yes, you need still omega n. What is the k? So from this only I found k is equal to 1. Omega n is equal to what? Omega n square is 25, omega n is 5 radian per second. Then what is 2 zeta omega n? 2 zeta omega n is equal to the coefficient of, yes, that is 5 into root 2, and omega n is already known 5. So this 5 and this will get cancelled. So what is your zeta then? Root 2 by 2. There is nothing but 1 by root 2. So root 2 by 2. That's the interesting point. So zeta becomes, fortunately this value, I will say for a reason, you will understand soon. 2 zeta, let me check that data. 2 zeta omega n is equal to 5 root 2. So 2 zeta omega n, okay, omega n 5 will cancel, zeta becomes root 2 by 2, that is 1 by root 2. That's wonderful. Zeta equal to 0.707. No resonance happens. No resonance happens. Then what will be the resonance peak? Zeta equal to, yes, this is not valid. So MR is going to become 1. That's a maximum. And resonance is not going to happen here. We're expecting the resonance. Unfortunately, resonance is not happening. Problem is, okay, wonderfully designed. Yes, it is going to have only maximally flat frequency response. Okay, what is a maximum value it is going to have means, okay, resonance is going to happen. So even omega r is equal to omega n into root of 1 minus 2 zeta square. If you put the zeta, then omega r will become 0. Resonance is going to happen only at 0. That is the maximum. So maximum is going to be k. That is going to be the 1 is the answer. That's a resonant peak. That's a wonderful problem. Okay, so there is no resonance happening in this. Okay, so maximally flat response. So MR is equal to 1 is the correct answer. Okay, so you can check once what is the answer you have given. He said resonance peak. So he actually surprised us by not giving any resonance in the system. Yeah, that's a very good problem. Okay. Yes, believe strongly. Unless in other ways we commit any mistake in the manipulation. Yes. Okay, then that's a best solution for this problem. Okay. Let me check only for that 2 zeta omega n once again, because he's asking resonant. I'm not getting resonance. Okay, but still I'm suspecting myself whether I committed any mistake. So 5 root 2. So 2 zeta omega n 1 alone. Okay, k is not influencing. Yes, k is 1. Omega n is 5. So 2 zeta, perfectly all right. Okay, so resonance is going to happen. In fact, these two expressions are valid only when zeta falls between 0 and 1 by root 2. Okay, there is no resonance in your second order system when zeta greater than r is equal to 1 by root 2. So the maximum will be your DC gain itself. That's a maximum. If they say resonance without resonance condition, that's a maximum. Okay, but anyway, he didn't go for zeta greater than 1 by root 2. He played at the boundary where the second order system is going to have no resonance. Okay, that is omega r will become 0, mr will become k itself, DC gain itself. That's a very good problem connected to the fundamental of second order frequency domain response. Next problem is it is given the characteristic equation of a system is given. Okay, so s cube 3s square plus 4 plus ks. And yes, I'm just showing the speed. Okay, at what speed you have to play in the exam as well. Okay, yes. So this will serve as an example for a right aspirant who knows everything. Okay, so feel that way. So then I'll begin with this. So s cube a square as per the RH criteria, s power 1, s power 0. That's all. Okay, so it's a third order characteristic equation. First two rows will be filled by the coefficients of the characteristic equation itself. Yes, first row beginning with is power, so it's 1. Second element 4 plus k. Okay, right? Only coefficients of odd power terms. Then second row will be due to even power. There is going to be 3 and then 2 plus 2k. Okay, right. That's all. Then the bound on value of k for which the system would be stable is okay. Yes, then already we have answered one problem in 2 marks. It is similar to that. Okay, so you learned something. Where what is the learning? You went by trial and error. Do the same thing here as well. Okay, yes. What is the expression? So 3 into 4 plus k is going to be 3 into 4 plus k minus 2 plus 2k divided by 3. Okay. And this will be, so take this as x and this will be 0 based on the 0 0. Then this x into this divided by the x after 3 into 0, that is 0. So divided by the x will give the same 2 plus 2k. So these are the first column elements. So remove the x. Now you got all the first column elements. So there should not be any sign change in the first column elements if you want the system to be absolutely stable. That's a requirement. Okay, yes, for the condition now. What is the condition now? So this is already positive. There should not be sign change. Okay, your element may be negative, no problem. And what is the sign of this? Positive. Sign of this positive. Therefore, it must be positive. It must be positive for stability. The bound on value of k for which the system would be stable means. So first take the easy bound, that is 2 plus 2k should be greater than 0. That means 2k should be greater than minus 2. So k should be greater than minus 1 is the first call. K should be greater than minus 1 is the first call. It is there. Okay, right? So k greater than minus 1, system may be stable. Okay, so now let me go for k greater than minus 1 means what else is the upper bound? Is one option I missed, I guess. Let me check. What is the option I missed? Yes, k greater than or equal to plus 1, the option I missed. Because we're playing with the option. So the last option is k greater than or equal to plus 1 is the option. Okay, now let me check in that aspect also. So let me set k is equal to 1. Check what happens. K is equal to 1 means, so this is k greater than minus 1. It is positive. Okay, so now let me say k equal to 1. K equal to 1. This is positive for sure. This is positive. Okay, then k is equal to 1 here means it is going to be 3. And then 3 into 5, that is going to be 15 minus. Okay, k is equal to 1 means it is going to be 4. So it's positive. Okay, right? So yes, for this value, it is positive. So k greater than 1. So k already greater than minus 1. This is stable. So let me take k equal to 0, for example. K is equal to 0 means what is happening? This is positive, no doubt. K is equal to 0 here. K is equal to 0 here means, yes, it is positive. Okay, right? It is positive. Yes, k greater than 0, it is positive. Then any lower upper bound, so that is a lower bound. Okay, k greater than minus 1 is serving as a lower bound. Yes, k greater than minus 1, this is stable. This is also this is positive, this is also positive. Then let me check for k is equal to 8. For example, k is equal to 8 means it's going to be, it's by default it is positive. Then k is equal to 8 means, yes, 4 plus 8 12. So 3 into 12 is, then it's automatically, so that means 3 plus 4 k. I'll take this way, 3 plus 4, that is 12 plus 12 plus 12 plus 3k minus 2 minus 2k should be greater than 0. What is that? I think we'll go for a number. Okay, it's easy only. I thought it is second order. Okay, it's simple only. So it's 10 plus k greater than 0. That means k greater than minus 10. It says k greater than minus 10. Yes, already. Okay, fine then. This is overridden. Okay, this is the case. So that's our answer. So k greater than minus 1 itself, the system is absolutely stable. Okay, that's a very simple problem. Okay, so because of the last problem, we had a second order, thought of second order, but it is concluding instantly by expanding this. We should have went straight away with this, and then two conditions to conclude: k greater than minus 10 and k greater than minus 1. This is overridden. So that's a condition for stability. So any other k will satisfy. So that's answer. So C is the answer for this problem. Yes, then the final one for this video. So what is given? The phase difference between the input signal and output signal voltage of a transistor connected in common emitter configuration. Yes, I'll give directly the AC signal, AC analysis perception of a common emitter. Okay. AC analysis perception of a common emitter. For simplicity, I'm not talking about the biasing conditions. That is a DC analysis. So let me take the circuit will look like this, assuming even if it is a potential divider biasing, it will be like this. That's your RB. So here we have the signal to be amplified. That's your VIN connected to the base. As of now, I'm not talking about coupling and bypass capacitors. Okay, so assume they are there in the circuit and they did their role. After that, whatever the circuit I have is the circuit for AC analysis. That's a small signal equivalent of the BJT. This is the base terminal. This is the emitter terminal. And here in the collector terminal, we have the collector resistance RC. Okay, yes. This is how we get the equivalent circuit. If we know the expression for common emitter gain, it's over. Okay, right? So this is your V0. So if you know the expression, and transistor is a device capable of transferring current from one resistance circuit to another resistance circuit, means so it is going to transfer the current from small re to capital RC straight away. If you know the point, then it's V0 by Vn equal to minus RC by small re, you can say. I'll just prove it. So take this point, that's Vn. As per the small signal equivalent, this potential difference is 0. Therefore, this point potential is also going to be Vn, and that is going to be the voltage across small Rg, and that is going to make the emitter current of Vn by small Rg. And by default, we assume beta very, very greater than 1. The same current is reflected in the collector. Ic and IE will be equal when beta is large. Then you will end up with Vn by small Rg. That is going to make a drop here as Vn by small Rg into capital RC, and the top potential as per the AC analysis is 0. VCC will be grounded. So from 0, you are losing this. So V0 is going to become this. What is that? Minus Vn by small Rg into RC will give this expression. That's your voltage gain of a common emitter configuration. Yes, problem is with respect to this only. So what is your V0? V0 is going to be Vn divided by Vn into RC by small Rg at an angle minus 180 degree. That means output will be having 180 degree phase shift comparing to Vn. So Vn may have angle of 0. That means Vn will begin with positive off cycle, whereas V0 will begin with negative off cycle. If one knows this, then straight away he will connect it. That's your amplified output signal. Okay, that's all. Yes, what is that? You can choose it. The phase difference between input signal and output signal of a voltage, output signal voltage of a transistor connected in common emitter will have 180 degree phase shift. That's a correct answer. You can go with the gain itself. Once you remember the gain, straight away, okay, you know the expression connecting V0 and Vn. There itself, we can see the phase shift between V0 and Vn. So what will happen if the question is for the common collector, or if it is for the common base? Common base, the gain will become V0 equal to same gain RC by small rp into Vn. You will get that's going to be in phase. What about for common collector? Common collector also going to be in phase. So common base output will be in phase with the input voltage. Common collector also going to be in phase with the input voltage. Only in common emitter output will be out of phase with the input signal by the 180 degree. That means positive of cycles in the input will make negative of cycles in the output. Okay, that's a very interesting basic of common emitter amplifier, single stage using NPN. Yes, hope you're enjoying the content delivered. Okay, so you're able to understand everything. Okay, so you can still, if you have any doubts, you are most welcome to write. Okay, so as a comment in the comment session. Okay, so with this, let me conclude the video. We'll update you with one more video. Okay, thanks for watching and do subscribe our channel. Okay.